Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.3.3. Groups that work component-wise. So you see these are ordered pairs of elements from this set where we have pairs, meaning we take an element in here, comma, an element in here. This is a Cartesian product of sets. So we take all our options of having 0, right? And then we pair those up with things that are in this set, which are 0, 1 through 0 through 3 bar, and we distinguish them by different bars. Now, we can actually define a group operation, addition, on this, knowing that z mod 3z is a group under addition, and z mod 4z as itself is a group as well under addition. And if we take a Cartesian product, look at this table, we actually again get a group. Because the additive identity in this group actually ends up being 0, 0. Because if you add 0, 0 to anything, it gets itself. Notice, so you just have to check, do we have the identity in each column and row exactly once? You can double check it, and you do. This operation actually comes from the operation here and here, just in commas. And so actually we, again, get associativity kind of transferred nicely from that pairing, and that can be checked. But so we have associativity, we have inverses, it's closed. We again get a group, and operations are done component-wise. Here's just an illustration of how that can work. Okay, so and kind of thinking about what the addition operation looks like, it looks something like this. We're doing addition just in each component one at a time. All right. Now let's look at this next little subsection: multiplicative inverses and component-wise groups. Well, okay. Now there was a little theorem up there in another subsection that showed that if we take away everything that doesn't have a multiplication inverse, then we'd have a group. Now, what is a multiplication inverse when you're doing component-wise? Well, notice how we got the additive inverse. We just took 0, 0. It makes sense. Maybe we take like 1, 1. Because if we take 1, 1 and we multiply it to anything, we should get back itself because we're doing it component-wise to itself. So we look down those. Let's just look down these columns. Not all of these columns have 1, 1 in it. This one doesn't, for instance. So we're going to have to take some columns out. And there was a theorem back there which actually said if we did that, we would have we would actually be able to have a multiplicative group. So let's take a look at that and see if, yeah, okay. So here's just some results talking about that. So let's take a look, just go back here and look at this. So multiplication. So this is multiplication defined for the set. And notice, okay, so this is a multiplication table right here. And notice in this multiplication table that I guess that's is what we need. So we have 1, 1, right? And it needs to be multiplication in order to think about this. And we look at the rows and the columns, and we're going to have to throw some out. Okay, we throw some out and we have a nice group now. How do we find inverses? Just component-wise. Like, what's the inverse of this? Well, we just have to take the inverse in each part, and then we're good. So here's a question then. How many elements are in this set, right? Where we threw out, so we take all the pairs, we're throwing out things out that don't have inverses. Well, essentially, what does this mean? This means this is the pairs of all things where each thing has an inverse. Well, you think, how many inverses are in this one? How many inverses are in this one? How many things have inverses in here? How many things have inverses in here? Well, 0, 1, and, well, let's see. No, 0 doesn't, but 1, 2 don't share any common factors with 3, so there's 2 in here. So that's the size of this set. The size of this set is 2. Now, what's the size of this set? We think, what doesn't share a factor with 4? Well, that'd be 1 and 3. So there's 2 there. So 2 times 2 should be 4. In fact, if we look at it, 1, 2, 3, 4, they're all there, all those pairs. So we get that there's 4 elements in this set when we take out things that don't have inverses. And this is just a little statement which just verifies that. Remember that these just mean the size of that particular group. Um, okay, and that concludes this little subsection. Thanks for watching.